So the next slide shows a points list that we'll use for our 3 sample function groups. Notice that on the input side, I skip the first 3 inputs and start with input instance 3. So there's supply return mix and outside temp as well as the duct static input. On the digital output side, there's a fan output to enable the fan, 2 stages of cooling, 2 stages of heating, and then 2 analog outputs, 1 for a VFD to control the speed of the fan and 1 for an economizer to modulate the damper position to meet a mixed air set point. And so then I'll go through, actually I talked about this briefly with the analog and binary values before about the IO points being automatically discoverable. And during our programming exercises, here's some of the analog and binary value points that we'll use. So we want to be able to change the duct static set point from the front end, change the cooling and heating set points from the front end, reserve a binary value to connect to the IntelliFront schedule so that the IntelliFront schedule can command the unit on and off. That would be a read-write binary value. And then the high duct static alarm would be a read-only binary value. So when the static pressure gets too high, then we can trigger an alarm that IntelliFront can show in its alarms app. So I'll show you the sequences that we're going to program, and then we'll actually go back, put the points in our controller, and then actually do the programming ourselves. So the fan sequence, and these are fairly simple just to get you started. If you have questions about making them a little more complicated to handle different types of conditions, we should have time to do that. So we're going to write to a remote schedule a binary value. When we write a 1, it'll turn on. When we write a 0, it'll turn off. And that gets linked to the interlock handle of the PID icon. So when the schedule's off, the PID essentially stops calculating. When the schedule turns on, then we'll look at the duct static pressure input, run it through a PID calculation to control the analog output. When the interlock is true, then the binary output from the PID icon will turn on, which will enable the fan. This analog value will let us change the static pressure set point from the front end. And then we'll add a counter to keep track of the fan starts and run times. We'll add a notify instance to see if the duct static pressure gets too high. And then when it does get too high, we'll link it to this binary value so that IntelliFront can see that and log an alarm. I'm going to skip past these PID loop slides. So it's just some detail for the PID object that I think is helpful. We'll refer to this more while we're programming the controllers. Cooling and heating sequences, we're just going to do a simple return error control just so that you can see how the sequence object works. So we're going to interlock both sequences to make sure that we have some minimum static pressure. And then we're also going to check the return error sensor to make sure that there's not a wiring error, because if the wire was cut, then normally the return error temperature looks very low, which could trigger the heat to run indefinitely. We generally don't want to do that. If the return error temperature wires are shorted, then that tends to show a very high temperature, which could cause the cooling to run indefinitely, and we typically don't want that. So we'll use that to interlock to both the cooling and the heating sequences. We'll have independent cooling and heating set points that are stored in the analog value object so that we can change them from IntelliFront. And then on the cooling side, we're actually going to program it as if there were 3 stages of cooling. So stage 1 we'll reserve for the economizer if the outside conditions are good. And then the number 2 cooling sequence output will link to mechanical cooling 1. The stage 3 from the cooling sequence will link to mechanical cooling 2. And then heating, we only need 2 stages. There's no equivalent of economizer on the heating side. And then the last one is the economizer sequence. We're just going to do simple dry bulb control to look at the mixed air. When the outside air conditions are good and there's a call for cooling, and the fan output in this case is on, then we'll run this PID calculation, and we'll actually set the minimum position in the PID calculation. And so when the fan is on, the analog output will drive based on the PID calculation. When the fan turns off, we're going to program the analog output to ignore the PID value and just go to the closed position. So those are the three programs we'll build today. And so a good starting point is just to name your IO points, and remember that we start from input instance 3. Those of you that are staying on to do IntelliFront, it will be better if you follow my naming convention exactly, so that when we see the points in IntelliFront, it'll make it a little bit easier to get them added cleanly to the database. If you don't get them quite right, we can still do it. It'll take a few more mouse clicks. So now we're going to go name the points in the controller. So I find that easier to do on the Objects tab. And so Object 3 is for outputs, Object 5 is for inputs, Object 15 is for analog outputs. And so I can start with the input, since that's on the left side of your page. So starting from input instance 3, you can just click on the input name here, and input instance 3 was it supply return mix. So I could just type in supply air temp. You could also copy that if you want to not have to type it all out. You could do a right-click copy or Control-C. And then if you arrow down to the next instance, then you can click on its name, like input 4, and just do a right-click paste or Control-V. And then you can change supply to return. So that's one way to save you some typing when you're naming your points. Another way to do it, if you click on your named input like return air temp on here on the left in the objects tree, you can right click on that instance and select copy, then go down to the next one and do a right click paste. And then it already has, it's an exact copy, so then you can just change the word return to mixed. So those are a few things to save some typing. I also mentioned you can use the up and down arrow keys to advance up and down through the tree if that's faster than mousing back and forth. So then I got duct static, and then I have outside air temp. Notice that when even after you name the instance, up in the upper left corner above the Objects and Functions tabs, it shows you the name of the instance, and then up a little further, it shows you the object index reference. So supply air temp is input instance 3. So you can kind of look in that section to make sure that your names are associated with the right instances. So input instance 3 is supply temp. And the rest of those look good. So then I'll go to the output, object number 3. I've already named output instance 0 fan, so that one's fine. Then I'll go to do cooling 1. You could do the same copy paste type thing. I'll just type them. The names are not that long, but I did want to show that to you because depending on how quickly you type, that might save you, some valuable time. And then analog output, the first one is called VFD, and the second one's called economizer. So I think those are all the name points. There are 5 outputs, there are 5 inputs, and there are 2 analog outputs. All right, so then we can move on and start building our fan sequence. So what I will do is switch to the Functions tab. And we've actually already started building our fan group. So you can go to the group you named fan control, since it already has the fan output. To break a handle, because we're not going to be using this internal schedule, to break a handle, you go to the endpoint coming in from the left and just do a right click and release. and that will break the line. And then to remove an icon from the group, you could just do a right-click delete. Be careful, though, because clear and delete are different. Clear resets all the settings for that icon back to 0, but doesn't remove it from the group. And delete kind of does the opposite. It removes it from the group, but doesn't change any of the settings. So delete's all I really need here. And then in terms of dragging the icons on, I'm going to not drag on the counter and the notify and the binary value as we get started, because they're not needed for control. It'll just make it a little simpler to get started, and then we can add those as we go. So I'm actually going to drag this down to my lower monitor so I can see it while I'm working. There it is. And there's it. Okay. So with your object box positioned in your preferred location, and by the way, if you ever close the object box, you can X out from the top right. If you ever need to get it back, just right click in the larger workspace on the right and select Add Objects at the top, and it should reappear in the last known location. So there should already be an input named DuckStatic. So I'll pick the input object and I'll drag the input named DuckStatic onto the screen. I'll then go back to the objects box and find BVL for binary value and drag the 0th instance down below. I'll next go to the PID object and drag the 0th instance on the screen. I already have the digital output, so I'll next go to the analog output object, ANO, drag the instance named VFD below the fan, and then finally I'll go back to my objects box and find AVL for analog value and drag the 0th instance onto the screen like that. So that's a total of 6 icons. Okay, so you can see that some of the icons have the red circle with a slash, so we want to enable those. And you could go to each one individually and do a right-click enable. What I tend to do is select a group of them and enable them all together. And there's different ways to do multi-select. The way I usually do it is to just draw a rectangle around all of the ones I want. And if you select one that's already enabled, that's okay. So once you have multiple icons selected, then you can right-click on any one of the icons and select Enable, and they all become enabled. Another way to do multi-select is to hold the Control or Shift button down on your keyboard. Either one does multi-select. And then another way to do multi-select is just to right-click Select All, which selects every icon, and then you could right-click Enable. So you might find that easier to save a few clicks and save a little bit of time, but again, you can certainly enable them individually as well. So our DuckStatic input, we would want to, we have to configure it to read as pressure, because so we'll just make some notes here. I'll just, let's see, today's 10/28/2020. So I'm going to say the DuckStatic input is 0 to 5 volts DC equals 0 to 3 inches water column. So if that was the case, I would go to my DuckStatic input, and then physically on the controller, I would remove the pull-up resistor. So I mentioned that I'll just show you in the help files, help ASIC3 INST for the 9540 is the installation guide. And let's see, it's under wiring, input, pull-up resistors. So below the relays, there are 16 pull-up resistors, one for each of the 16 inputs. The one on the left is labeled R1 for the first input. The one on the right is labeled R16 for the 16th input. And by default, they all have a 3.32 k ohm pull-up resistor, which works fine if it's a single binary input. or a thermistor input. But for an active input, when we're like a 0 to 5, 1 to 5, 4 to 20 type input, here on the, if you go to the required pull-up resistors section, it'll kind of tell you generally what you're going to want to do. So if it's a 0 to 5 volt DC input, we want to, no pull-up means remove the pull-up resistor for that input. So that means in this case, since our input is, our duct static pressure input is input instance 6, that's the 7th physical input. And so we would go find our 7, carefully use our needle nose pliers to remove the pull-up resistor. To be totally safe, it would be best to power down the controller. If you're careful and don't short anything together with your needle nose pliers, you can take the pull-up resistor out while the controller has power. And then most people end up having some little plastic storage box that they store the pull-up resistors that they take out, so that if you ever need one to reinstall later, you don't just want to throw it away because it might be helpful. They're not expensive, but if you don't have one, then it might be expensive in terms of the time it takes to get another one. And so physically, you'd remove the pull-up resistor because you're supplying 0 to 5 volts DC into the controller. And then I just went into the properties of my duct static icon with the right-click properties. And so it's already been named. The input type is analog, so that's correct. If you click on that box, you can see some of the different choices, but analog input is correct for this type of input. And for an analog input, there's a convert type, which basically says, how do I convert the voltage to some, engineering type functional units, in this case, inches water column. So for linear input, 0 to 5, 4 to 5, 1 to 20, 0 to 5, 1 to 5, 4 to 20 milliamp type inputs, if you click on that convert type field where it says raw in all capital letters, pops up a list. At the top is a bunch of thermistor options, which is not what we have since it's a pressure input. But if you scroll down a little bit, there's one called sensor 2, and that's the one we want to use for an active input, like a 0 to 5 volt type input. Once you choose sensor 2, then the script running in the background shows you the kind of the scaling parameters for that input that we'll get to here in a minute. But first, there's a units section. And so if I click on the units box where it says raw, there's a predefined list here. And so I'm going to choose 0.01 inches water column, remembering that our controller does everything in whole numbers, because I don't just want to see 0, 1, 2, or 3. I want to be able to see things down to the 100th of an inch. So 0.01 inches water column as the unit. And then in this input conversion field setting, it shows how we can scale the input. So there's some hints here. For 0 volts, enter 0. For 5 volts, enter 4095. So raw minimum is 0 for 0 volts. Raw maximum is 4095 for 5 volts. And then the engineering unit says, at those voltages, what do you want the present value to be? So at 0 volts, I want to see 0 inches of pressure. At 5 volts, I'm going to enter the engineering units as 300, where 300 represents 3.00 inches water column. And so our controllers themselves, since we don't have any wiring connected to them, the pull-up resistor is in place, which is fine. In the live training class, we would normally connect a potentiometer to the input, and then we can spin the potentiometer to adjust the present value. Since we can't put our hands on the training kits that are remotely accessible, we're just going to end up overriding the input to adjust the values and see how the controller responds. So did everybody choose sensor 2 and enter the scaling parameters?
Yes.
Yep, good. Okay. So now that
Mike,
that input's reading in, yep.
This is James. Can you jump back on? Because I'm still having trouble catching up to where you're at. I mean, I was listening to you guys, but
Okay.
6 objects, I
Go
did
ahead
all
and
the
share.
inputs and outputs, but I'm not seeing the same things as you when I'm pulling them in.
Okay, so so the duct static input, I think is down at the bottom of your screen right now. So drag that up.
Yes.
Move the VFD out to the right of the PID, down lower right. Yeah. Okay, then you're missing a binary value. So hit your drop-down menu for the objects box and find BVL for binary values. It's in alphabetical order. Go up to the B's, binary value. Yep. Drag one of those below duct static. Just down below would be a little bit better. Yep. And then the last one you need, go to the objects box and pick AV. Oh, yeah, you close the box, so right click. Yeah, there you go. So scroll up to analog value. That's analog out. I want analog value. Okay. And then drag the 0. Drag it down kind of lower right below the VFD or near the VFD. Yeah, that's fine. Okay, so that enable all of the icons that have the red circle. So you can either do it individually or select all. You can just select enable there. If you're going to do select all, you have to right click where there's nothing. Yeah, so yeah, we're going to get rid of the red circles.
Yep.
Do that on the PID itself. The PID still has the red circle on it. Yeah. So now let's look at your duct static properties and see how if that one's set up for scaling. So the input icon called duct static, go to the properties view. So change the convert type to sensor 2. Just left click on convert type where it says raw. Scroll down to see sensor 2. And then raw maximum 4095, meaning 5 volts.
Yep.
No, the raw maximum to the, no, I don't think that's the right one.
Raw max.
Yeah, to the left. Yeah, that one there. Yeah, so there's the 4095.
Yes.
And then the box to the right of 4095 is where I put in the 300. So that means 3.00 inches. And then the units below the convert type where it still says raw, pick 0.01 inches water column. Near the top, scroll up. It's like the 4th one from the top. 0.01. 0. Yeah, that's the one. Yep.
Thank you.
Okay, I think that's good. Yep, no problem.
Yep.
So I'll share my screen again. And so now the input has been configured to read in inches. So then I can right click and drag and connect it to the input handle of the PID icon. So I'll go to the value, black square, right click and drag, drop it on the input square. I hear the bell ring and the line changes to blue. Release. Now I see those connected. And then for this binary value, I want it to be my remote schedule. So I want it to default on. So from the left side handle, let me go back to this slide. To get this little gray box, you just right click and drag from the left square as if you're going to drop it on another icon, but you'll see a red pound sign above the icon. Just drop it on that red pound sign and it'll ask you to enter a number and you can just type in the 1, meaning on. So from the left side of the BV icon, I right click and drag. There's the red pound sign right above the BV icon. I drop it on that red square, on that red pound sign. Ask me to enter a value. I enter 1, and then I get a gray box with 1 so that that binary value instance defaults on. And then I can take that output from the right of that binary value and right click and drag to connect it to the interlock 1 handle. INTLK1 is the 3rd square from the top left of the PID icon. So right click and drag, INTLK1, there's the bell and the blue line. And so now those are connected. I can go to my binary value and give it a name by going to the binary value properties. So if I go to the BV, go to properties view, I can call it remote schedule. And when you click to change the name, that it says binary value string 16 at the top of the box. and that means I can enter up to 16 characters. So remote schedule fits within that 16 character limit. And so there's that one. I think this controller acts a little strangely. I think coming out of your right side, does yours have a red value of 1 where mine is showing 0?
Yes, mine says 1.
Mine says
Yeah,
0.
this
Ours says
controller.
1 right now.
Okay, if yours does say 0 and you want it to say 1, I'm not sure why they're behaving differently. But if you go to the Objects tab, and then that starts out at the System Object, just click that Reset Action button kind of in the lower left of the System tab, and that will reset the controller, and then it should start up with a 1. And so then once it resets and the clock starts ticking in the upper right corner here again, you go back to the Functions tab, pick your fan control group, then you should have a 1 there. I'm not sure why they behave differently. I might take a look at that. Let's see. Check binary value for remote schedule should switch to 1 when special handle is made. Okay, so now that means that the interlock handle has been established at the PID icon, but now we can go into properties view. Actually, we can make the other output connection. So take the binary output BO and connect it to the VAL handle for the fan. And then take ANO from the right side of the PID icon and connect it to the value for the VFD. I'm not going to connect the AV just yet because while we're programming, we'll look at some of the different settings, and that'll help us understand where we're going to connect this AV to. So if I go to properties of the PID now, I usually just start at the top and work my way down, look at the green settings and decide if they need to be changed. So I can give my PID loop a name like VFD PID. And then if I go to the slide, this is where I mentioned that there's some information here about the different settings that I think you'll find helpful. So the first setting there said direct acting. That's actually on the second of the PID slide. So direct acting no is a reverse acting loop, which means as the input goes up above set point, then we reduce the analog output. That would be typical for heating. If our temperature went too high, we reduce the analog output to reduce the heat being generated. If you set direct acting to yes, then it's a direct acting loop, which means as the input rises above set point, then you increase the analog output signal, typical for cooling. So like if your chill water valve set point was, or your supplier set point was 55 and the supply temp was 60, then it's higher than the set point. Usually you want to increase the analog output to open the valve to get more cooling. So in the case of fan control, it would be reverse acting. If the pressure gets too high, then we reduce the signal to slow down the fan. So direct acting would be no there. And just like in the ASIC ones, the text describes the current setting of the checkbox. So unchecked and no is what I want here. The next setting says absolute PID enable. If I go back a slide, then it says absolute PID enable equals yes. Often works better for slower loops, like room temperature control. If you change for a VAV system, if you were to change or move the damper, the room temperature itself is going to take some time to change. That's not going to respond that quickly. As opposed to if you move a chill water valve, then the supply air temp tends to change fairly quickly. And I think duct static pressure tends to fall into that group too. If we change the speed of the fan, we should see the static pressure input change fairly quickly. So I have found that absolute PID enable equal to no. That's what we call the incremental calculation. That tends to work better for something like static pressure. So absolute PID PID Enable will be equal to no. Control set point occupied would be our static pressure set point. So if our static pressure set point was 1.5 inches, knowing that our input is also in hundredths of an inch, then for 1.5 inches, we would set control set point occ to 150. And I think that's here in the slide. Actually, I didn't mention that one. But there is also a unit setting. The controller doesn't really care about the unit setting, but it's helpful for somebody who's programming the controller or looking at the program to understand where to mentally put the decimal. So in this case, the unit should be 0.01 inches water column. And then here on the lower left of the current status tab, there's a bunch of checkboxes for kind of the optional handles. So since we connected to the interlock 1 handle, we do want to enable the interlock 1 handle by putting a check in the box. And that script running in the background, all the associated settings are gray until you enable it, and then those values become enabled without the gray text. And then it'll show you how that input or how that handle is evaluating. So remote schedule is on, so that's why it says yes. If you had both interlock 1 and 2 enabled, then this interlocks OK would only say yes if both of the enabled interlocks were true. And I mentioned earlier that the binary output turns on whenever the enabled interlocks are true. So when the schedule's on, the binary output from the PID will be on. When the schedule's off, the binary output for the PID will be off. So moving on to the PID Loop Setup tab, there are some settings here that we've already set. So the first new setting is really the Calc Time, because we've already set the input handle in graphical programming. We enabled it in graphical programming, and we chose the absolute PID Enable and direct acting options on the previous tab. So going to the slides here, it says Calc Time is the interval between calculations. And I like to set that based on the response time of the equipment, because when I am using my PID calculation, I like to change the analog output and then wait for the system to respond to that change before I make my next change. So that'll be somewhat dependent on once you are connected to equipment to see how long the input takes to really make a significant change based on an analog output change. So we don't have any equipment connected to ours. We're just simulating here. So I'll enter a calc time of 15 seconds. And then the next setting is throttling range. That's in the same units as the input. In this case, that would be hundredths of an inch. And this is one of the settings that you'll change as you're tuning your PID loop once you get everything wired up to the controller. But as far as an initial setting goes, I like to think of it as how much error would I want to have before I went to 100% signal from the proportional component, where PID, just a little background, stands for proportional integral derivative. It's a calculation that somebody thought of about 100 years ago, where the proportional part of the calculation is related to the current error, where the error is the difference between the input and the set point. The integral is related to the summation of the error over time, and then the derivative is related to the difference between the current error and the previous error, meaning the error from the previous cycle. And so in this case, if I wanted to say if I was an inch below set point, then I should go to full speed. Then I can enter a throttling range of 100. And there's a note there on the slide that says when you're tuning your loop, if the PID loop, you notice, is the changes that it's making are relatively large, larger than you'd expect or would want to see, then if you increase the throttling range value, then it'll kind of slow down the loop, flatten the response. And if you're if the PID loop's kind of sluggish and not updating the analog output changes are not large enough, then you can decrease the value and it will become more aggressive. And so I usually, when I'm increasing, I just double it. If I'm decreasing, I cut it in half. And at some point, you kind of see it switch from either being too aggressive to too sluggish, or too sluggish to too aggressive. And then you've kind of established that you can narrow down within that range, and then you can kind of tweak it a little bit further. We can't go to that degree here in a simulation, but those notes you might find helpful when you're connected to a live system. So I just put in 100 to start. Maximum range is the next setting here. And on the slide, it says just set to 255. That just makes it easy. That's related to the, somewhat related to the resolution of our analog output, which can take 255 steps as they go from 0 to 10 volts.